What is debugging? You're working on a software project when suddenly something goes wrong. Maybe the application crashes. Maybe a button stops working. Maybe your API becomes unusually slow. Or perhaps your program runs without an error but produces the wrong result. This is where debugging begins. Debugging simply means finding out what went wrong, understanding why it happened, and correcting the code without creating new problems. Claude Code can help make this process easier because it can examine your project files, follow the logic through your code, review error messages, and help you identify possible causes. But Claude works best when you give it specific information. Instead of simply telling Claude, "My program doesn't work," give it the exact error message, explain what you expected to happen, describe what actually happened, and tell it how to reproduce the problem. A useful way for beginners to understand Claude Code debugging is through 3 simple stages. Isolate the problem. Analyze the cause. Fix the code and check for regressions. What problems can debugging solve? Debugging isn't only for applications that completely crash. Many different software problems can require debugging. Your application might display an error that prevents it from running. A calculation might return the wrong answer. A website button might work sometimes but fail under certain conditions. An API might become slow when many users connect at the same time. Your application could have a memory problem that gradually reduces performance. You might also have configuration problems, database connection failures, or problems communicating with another service. These bugs can look completely different, but the debugging process remains similar. First, determine exactly where the problem occurs. Then understand why it occurs. Finally, make the smallest reasonable correction and verify that your change hasn't damaged something else. Claude Code can assist throughout this entire process. Stage 1. Isolation. The first stage is isolation. Isolation means narrowing a large software problem down to the specific area of code responsible for it. Imagine that your application contains hundreds of files. You discover that customers sometimes receive a connection timeout. Without more information, Claude would have to search through a huge amount of code and make assumptions about where the problem might be. Instead, provide evidence. For example, rather than saying, "My API is slow sometimes," you could tell Claude, "I'm receiving a connection timeout after 3,000 milliseconds at pooled acquire. It happens when more than 50 users connect at the same time." Then provide the complete error message and stack trace. Now Claude has something specific to investigate. It can follow the call path, examine the files involved, and help narrow the problem to a particular function, configuration setting, or section of code. This is one of the most important debugging habits to develop. Start with the exact error rather than a vague description of the problem, giving Claude the right information. Once you've captured the error, give Claude enough context to reproduce and understand it. A good debugging request can include 4 basic pieces of information. First, provide the complete error message and stack trace. Second, explain how to reproduce the problem. Third, tell Claude what you expected the program to do. And fourth, explain what actually happened. You can also mention recently changed files, your development environment, and anything unusual that happened immediately before the bug appeared. For example, you might tell Claude, "The checkout page worked before yesterday's changes. Now payment fails when 2 discount codes are entered. Here is the error and stack trace. Find the files involved and explain where the failure begins." Notice that you aren't immediately telling Claude to rewrite your application. You're asking it to investigate first. That separation between investigation and modification can make debugging much safer. Stage 2. Analysis. Once the problem has been isolated, the second stage is analysis. Analysis asks an important question. Why is this happening? Finding the location of an error doesn't necessarily mean you found its real cause. Suppose Claude identifies a timeout occurring in your database connection code. The timeout is the symptom. The underlying cause might be that your connection pool allows only 10 connections while your application is receiving many more simultaneous requests. Claude can examine related code, configuration files, and calling functions to help explain the complete logic flow. Instead of immediately asking Claude to change the code, you can ask, "Analyze this error and suggest 3 possible root causes. Do not modify the code yet." Claude can then present possible explanations. You can compare those hypotheses with the evidence before deciding what should be changed. This reduces guessing and helps you understand the bug before trying to fix it. From symptom to root cause. Think of analysis like investigating a leaking pipe. The water on the floor tells you there is a problem. But simply cleaning up the water doesn't repair the pipe. Software debugging works the same way. You don't only want to remove the visible error. You want to understand the root cause. Claude might determine that your database timeout happens because the connection pool is too small for the workload. Or it might discover that connections aren't being released correctly. Those are very different problems and could require very different fixes. This is why asking Claude to explain its reasoning can be useful. Ask it to identify the relevant files, explain the code path, describe the likely root cause, and recommend the smallest change necessary to correct it. Ending Part 1.